Okay, remember now, significant figures are used in calculations when you took measurements. We're going to do some conversions like number of atoms, number of moles, mass. That's different. Those are exacts. Like there's always 3 feet in a yard. Whenever you're using that, you wouldn't use significant figures. But when you're taking measurements, you need to use significant figures. And again, the reason why we do that, so your answer isn't more accurate than the measurements you took. Okay, so to review the rules, remember if it's a zero, zeros are the problems when you're trying to figure out significant figures. If it's not a zero, if it's 1 to 9, it's always significant. If you have numbers less than 1, you don't start counting the significant figures until you get to a non-zero number. So here I have 0.009. This only has 1. These are basically placeholders. Okay? If your number is less than 1, once you get to a non-zero number, okay, then they're all significant. So again, these would not be significant, these first 3, because they're placeholders. But now I would count the 9, the 1, and 2, and I would also count the 0 because it's after a non-zero number. Okay, so this one would have 4. So when I'm trying to figure out my calculation, if I'm trying to figure out the number of significant figures in this number, it would be 4. Okay, if a number is greater than 1, if you have zeros in between non-zero numbers, like if you have 101, that would have 3. So you always count the zeros if they're in between non-zero numbers. Okay, and then if you want zeros to be significant, add a decimal. Okay, if I write 9,000, that only has 1 significant figure. But if I write 9,000 and I put a decimal here, that has 4. Well, then you're like, so what's the difference? They're both 9,000. There's a big difference. This is an estimate. How many were there? There was like 9,000. By not writing the decimal, I didn't count. This, I counted and it just happened to fall on a 0. It doesn't happen very often. It's kind of like when you go to the store. You ever go to the store and it ends up on exactly $10? You know, it's usually 10.02 or 10.23 or something like that. But once in a while, it ends on 0, and that's what happened here. It landed right on 0. Okay, so that has 4. So if I want to make these numbers, these 0 significant, add a decimal. This one right here is also 9,000, but it has 6 significant figures. Sometimes we have equipment that's this accurate, and again, if it just falls on zeros, if you take the time to write the decimal and those extra zeros, they must be significant. So you can see these are all 9,000. This only has 1, this has 4, and this has 6 because of writing the decimals. Okay, so that number right there, this would have, these two wouldn't count, so would have just 3. This one, 2,000. No decimal, it only has 1. Okay, if I want these zeros to be significant, I got to write a decimal. This one, I got a number greater than 1. I got zeros in between non-zeros, and because this number is after the decimal, and I wrote it, I must have measured up to that point. Again, why would I write it if I hadn't measured? So I'd count them all. So this would have 1, 2, 3, 4, 5, 6. All 6 of these would be significant. Okay, why does it matter? When you're doing a calculation, the number of significant figures is very important. So you need to know significant figures. And these rules are also in your chapter 1 of your book. Okay, if you're doing calculations, okay, adding and subtracting significant figures, all you have to do is look at the decimal. Okay, if you have a number that goes 1 past the decimal, like 19.4, and you add it to one that has one number that goes 5 past the decimal, 6.29734. You're going to add them together like you normally would, then you look at your answer. And since the first one only goes 1 past the decimal, you have to round your answer so it goes 1 past the decimal. It's not the one that goes the farthest, it's the one that goes the least farthest. And again, when you report your answer that way, then you're making your answer as accurate as the measurements that you took. Okay, so here I have 7.8 plus 0.00456. Okay, so this goes 1 past the decimal, this goes 5. All right, so when I add them together, this is what I get. But if I reported my answer this way, I'd basically be lying. I'm going to give you an answer that's way more accurate than the measurements I took. So I can only go 1 past the decimal, so I'm going to have to round and lose all this. So it's still going to be 7.8. Even though I added this onto it, it really didn't make a difference. Okay? When you multiply and divide, it's the number of significant figures. Okay? It's not, you don't have to worry about the decimal anymore. It's the number of significant figures. So like here, I took 8 times 9.078. When I multiply them together, I get 72.624. Okay? This has one significant figure. This has 4. My answer can only have 1. So I have to take this number and I have to round it so it only has one significant figure. So I'm going to round it to 70. Now you might think, oh, it should be 72. 72 would have 2 significant figures. 70, by not writing the decimal, is still pretty close to the answer, but now I'm using the proper number of significant figures. Okay? So here's some calculations to perform. Okay, when we add these together, if you look, this goes 2 past the decimal, this goes 4 past the decimal, this goes 1 past the decimal. I have to round my answer so it only goes 1 past the decimal. And again, just add them like you normally would, but then look at your number and round it. Okay, same with subtracting. This goes 2 past the decimal, this goes 4 past the decimal, so I have to round my answer so it only goes 2 past the decimal. All right, if it doesn't go past the decimal, if it was 11, and then again, I'd have to round this to, like if it, in this case, it would have been just 9. So it's really important that when you're doing calculation with significant figures, you look at the decimal when you're adding and subtracting. More often though, you're going to do significant figures and you're going to multiply or divide. Okay, so in this one, 2.3 times 5, but because I put the decimal and these zeros, this has 4 significant figures. Okay, I measured up to that point, so I wrote down my zeros. Well, when you multiply these, you get 11.5. That's what you get when you normally on your calculator. But I can only add 2 significant figures, so I round it to 12. Okay. Here what I did, again, I have 4 significant figures times 2. You get 112.5. That's when you multiply these like you normally would. But I can only have 1 significant figure because 2 only has 1. So I'm going to round this to 100. Now you might think, oh, that's not, well, this only has 1 significant figure. So if you're doing proper calculations, you have to round it down to 100. Now I have only 1 significant figure, and that's going to be the closest number to that. I don't want to do 110. I don't want to do 112. Those have too many significant figures, so I have to round it down to 1. Okay. When you divide, same deal. Okay. This has 4 significant figures. This has 3. When I divide those, I actually get this big long number. And again, if I reported my answer this way, I'm basically lying. I'm saying, oh, this is how accurate it was, when I took my measurements, I wasn't that accurate. So since this one has 3 and this one has 4, my answer can only have 3. So I round it to 30.4. Okay. Here, the same deal. We got 3 and we got 2. When we divide it, we actually get 5.5. So that's just 2, and that's our right answer. If I needed this to be 3, let's say this had a 0 on it as well, then I'd write 5.50. That would make it 3. So you've got to adjust your numbers so they have the right amount of significant figures. Okay, and here's my favorite. 5 times 5, we all know that's 25. Not in significant figures, it's not. It's 30. Don't tell your math teachers. They'll get mad at me. But if you take 5 times 5 in significant figures, you can only have 1 significant figure, so you'd have to round your answer up to 30. Okay, I put a little thing on scientific notation, not this chapter, a little bit of next chapter, and a lot in chapter 3. We're going to start talking about the number of atoms, and it's a huge number. So we do calculations with scientific notation, and it's just a shorthand way of helping you. So you don't have to write out this big long number. Instead, you'd write 9.0, and then you'd go 1, 2, 3, 4, 5, 6. I had to move the decimal over 6 places, so that's why it's times 10 to the 6. This number equals this number. Okay? When you multiply, scientific notation, what you do is the numbers in front, you multiply them together. And then you just add the exponents. It's easier than writing out the whole number, writing the number like this, than doing just using your exponents, okay? When you divide the 2 numbers in front, and then you subtract the exponents, okay? So When you're all done, when you get your answer, let's say I did my calculation and I get 45.6 times 10 to the fifth. If I left it like that, that would be improper scientific notation. Instead, I'm going to move this decimal over because proper scientific notation, you have a whole number and then you have a decimal. Okay, so you move the decimal here. So I made this number smaller. I changed it from 45.6 to 4.56. And so I made this number smaller, so I make this number larger. So that's, these two equal each other. This one's in proper scientific notation. This one is not. Okay, so again, here's some calculations. If I take this, I'm multiplying now, so I'm going to take this times this, and then I'm going to add the exponents. So when I multiply these together, I get like 5.556 or something. I rounded it to have two significant figures, and then 9 plus 7 is 16. Okay, when I multiply these two, again, I take 5.46 times 9.36, and then negative 2 plus 5 is going to be 3. So this is what I get, 51.105. That's multiplying these two. And then again, negative 2 plus 5 is going to be 3. If I leave it like this, it's wrong. Okay, now I need to put it in proper scientific notation and significant figures. Okay, I got 3 here, so 5.11. I moved it over here. So again, I made this number smaller, so I make this number larger. So in proper significant figures and scientific notation, right there. Okay, when you divide them, okay, divide the two numbers in front and subtract the exponents. Okay, so when I take 4.52 and I divide by 7.8, oh, this should be 0.5, you guys. Sorry about that. I'll fix that later. You get, when you divide these, you get 0.57948 times 10 to the negative 6 minus 9 is minus 15. And so if I write it in proper scientific notation, now I have to move it over. I'm sorry, this is supposed to be 0.5, you guys. But anyway, I move this over, so now I made this number smaller, so I make this number larger. Okay? Over here, same deal. I divide these two numbers, and I subtract the exponents. 3 minus 11 is 14. And these just happen to be 2.24, so I don't have to convert it. Make sure you convert them when you're done. Okay, and again, this was 0.579. Sorry about that. When I move this, I made this number 5.8, so I made this number bigger. So then I make this number smaller. So whatever you do to this number, you do the opposite to the exponent. This is improper scientific notation and significant figures. This is as well. So you don't want to leave it in the wrong form. Move that decimal over, and I better fix that. Really sorry about that. Anyway, I think that's it. So what I'm going to do is I got some questions for you to do, some practice with significant figures and scientific notation. That'll be listed after this. If you got questions, let me know, and I will talk to you later.